I want to spend most of the time today working on some problems because we're getting closer to the midterm. And we have seen almost all of the theory that you need to know for the midterm. So it's time to really start practicing on as many problems as possible. So maybe we can go through 3 problems today and then do one last little piece of theory that we need before the exam. Okay, so these are all problems involving the first law of thermodynamics. Let me make a sketch here for the first one. Suppose we have a tank, and this is similar. It's not exactly the same, but it's similar to problem 395. So this is like 395, but it's not exactly the same because some of the data changes, and I think the end state might not be necessarily the same as the one we're doing here, but it's a tank. So suppose we have a rigid tank, and we know the volume of this tank is 5 cubic meters. And we know, let's see, we know the pressure. I'm thinking that we need to know, oh, okay. So we know the volume, we know the pressure, 0.1 megapascals. And we actually also know, so this tank is occupied by a saturated mixture. And so some of it is liquid, some of it is vapor. So let's say that this is the liquid and this is the vapor. And we know the volume that each of them occupy. So we know the liquid, let's call it capital VF. The volume occupied by the liquid is also given, is 0.05 cubic meters. And we know the volume occupied by the vapor, which is obviously what is missing to make it up to 5. So of the 5 cubic meters, 4.95 are occupied by vapor and 0.05 are occupied by liquid. So then what happens, and this is the initial condition, so then what happens is that we supply heat, and the process is going to be such that, so let's call this, these are all the conditions of state 1. And the condition or the requirement at state 2 is that all of the liquid is gone. Okay, so no liquid left, only saturated vapor. Okay, and this is what we need to find the amount of heat. So find, let's call this Q12, and that's what we need to determine. Okay, first thing you should do is what? To start getting an idea of what to do. What would you do first? You got to put something down on the paper. What would you do first? Huh? We could find the quality, and that's certainly a valid answer. We could find the quality. Something else that we could do first? No, I'm not talking about actually finding any numbers. Find what? Sure. Define the system. That's not what I had in mind. What's the system, or what should the system be? The control volume? No. What should the system be?
Everything inside the box.
Yeah, did I say what the substance was? Maybe I didn't. Yeah, water. So that's the system, water, the water in the tank. That's the best answer, the water in the tank. But I had something else in mind. What else can we do to get an idea of what's going on here? Right there at the end of the aisle. No, not numbers. You say that again? Yeah, let's do a PV diagram or a TV diagram, or that's always helpful. And many times you will also be asked to do it anyway. So let's say that we are going to do a PV diagram. It makes sense to make it P because we have the pressure, although we could, of course, get the temperature like somebody said. But so let's put pressure here. Let's make it in kilopascals because that's what the tables have. And specific volume here, cubic meters per kilogram. Okay, and so let's put a dome. And we're obviously inside the dome because we have liquid and vapor. We don't know the quality. Somebody said we could find the quality, and that's indeed true. We could find the quality. So let's put it somewhere here. We don't know exactly what the quality is yet. Don't be fooled by the volumes, right? Because the vapor occupies a lot of volume. So even though it's only 0.05 cubic meters of liquid, it's likely that most of the mass is actually liquid. But we'll put it somewhere for now. All right. So, and what is my process then? What direction does my process take? Yes? Straight up. Right? It's a constant. One thing to recognize is a rigid tank, so it has to be a constant volume process. And therefore, a constant volume process goes straight up. And where do I stop? Where should I stop? On the saturation line. So we'll stop right there. And now we have, at least on the drawing, on the PV diagram, we have identified the process. All right, so now we can just get some numbers. How can I find the quality? Let's put this pressure value here. This is 100. We don't know what this pressure is yet. We'll have to find out later. How can I find the quality? How can I find the quality? Lady right there, tell me. I think I asked you the other day, you already shook and no. We need a yes from you. How about you right behind her? How can I find the quality? Yes, but what do I do? Tell me what I do. Go to the table and do what? Which value am I looking for? What should I read in the table? Huh? I can go with this pressure, with 100 kilopascals, right, to the saturated table and read what? For, VF and VG. So table at 100 kilopascals, read VF, read VG. Right? And if you do that, you'll get the numbers. For VF, you will get 0.001043, and for VG 1.694. And these are cubic meters per kilogram. All right, so how is that going to help me to find the quality? How do I get the quality then? once I have that.
40 is V, G1 is VF over VFG.
Quality is V minus VF over VFG. We have everything, but we don't have V, little v, which is the one that you need in your formula. We don't have little v.
Use another one.
Okay, so what can I do? Can I get the mass of liquid, for example? What is the mass of liquid? The mass of liquid has to be the volume of the liquid divided by the specific volume of the liquid. Right? And I have that. I have all those numbers. So that will give you, for the mass of liquid, I'm going to round it up to 48 kilograms. And likewise, we can find the mass of vapor, capital VG over lowercase vg, and we have that. And that's going to be, again, rounding. It's going to be 3 kilograms. I'm just rounding to no decimals, but. So as I told you, indeed, most of the mass is liquid. There is really very little vapor. So therefore, what's the quality? From here, it's going to be 3 kilograms over 51 kilograms. All right? And that is some number. I didn't write it down, but we can get it if we need that. Okay, so state 1 is identified completely. Of course, this quality is a low value, is a low number, 3 over 50, over 51. But now we need to figure out where the end state is. So let's move this up. I still have a little bit of room here. So what do I know about the end state? What do I know about 2? Huh? It's all saturated vapor. Let's repeat that here. Only saturated vapor. And what else do I know? The quality is 1. That's the same thing as saying only saturated vapor. This is the same thing. Right? But what else do I know? Has to be the same specific volume, right? Same specific volume. So, and what is that specific volume, by the way? We can stick it maybe here, which is at 1, of course. The specific volume at 1 is, of course, the total volume, which is the 5 cubic meters divided by the total mass, right? Which is 51 kilograms. So that is about 0.1, right? Let me see. Yeah, let's round it to 0.1. So to make our life easier. So this is about 0.1 cubic meters per kilogram. All right. So that's of course V2. So state 2, I know that is only saturated vapor, and it has the same specific volume, and therefore is 0.1 meter cubes per kilogram. So I have 2 properties for state 2. That means that I can find, for example, I said, let's find this pressure. Suppose that we asked to find that pressure. How do I find that pressure now? Let's see if I have I think I have a copy of a table here. Pressure, VG. That's not going to make it there. So I want to show you this because you might have to do an interpolation. So if we go to the table, I'm going to go to the saturated pressure table. And what should I be looking for when I go to this table? What should I be looking for?
Specific volume is between the fluid and the gas.
Liquid and gas. No, I don't need to deal with the liquid.
You're looking for a specific volume of the vapor of 0.1?
Right. So I'm looking for a V sub G of 0.1. So if I come down here, of course, this is way too low of a pressure. I go all the way down, doesn't make it 800, so I got to keep going to the next page, which starts at 850 kilopascals, and now the volume starts to get where we want it to be. So, for example, if I just go to this, since we're just rounding things up, and this is very, very close, 0.099. I'm going to take that to be 0.1 for VG, and you should too if you're working on an exam. So that's my 0.1, and therefore that's my pressure, 2,000 kilopascal. If I want the temperature, I can get that temperature too. So we can then approximate from here, P2 is about 2,000 kilopascals. So if I want to complete this PV diagram, then I just put my 2,000 there. All right. And there is my P2, 2,000 kilopascals. So now state 2 is completely defined. But I still haven't answered the main question, which was to find the heat transfer. Right? So that's what I need the first law of thermodynamics. So if I write the first law, again, neglect potential energy, kinetic energy. So the first law is just, it'll be delta U equals Q12 minus W12. This is a rigid tank, so there is no work. So Q12 is simply capital, delta capital U. So Q12 is, always write it in terms of the intensive properties. So this is going to be the mass, which is constant in this problem. It's a closed system. So the mass times U2 minus U1. So we calculated the mass a while back. It was 51 kilograms. But we need U2 and U1. So of course U2 is the easiest of the two at this point. What's U2? I just go back to the same table I was just looking at. So if I go at 2,000, blow this up a little bit. If I go at 2,000 kilopascals, I just read that 0.01 there. The next number is way here to the right that I need is U sub G, 2,600. 2,600, that's my U sub 2, 2,600 kilojoules per kilogram. And what's U1? What's U1? Right there. Not the number, but how do you get it? Pass. Lady? How do I get U1? U sub 1. Nope. You know?
I'd go back to the table. We know the pressure.
Go back to the saturated table that we went in at the beginning at 100 kilopascals, right? And read UF and UG, right? So this is UF plus the quality that we calculated in the first part of the problem, UFG. So all of this comes from the table at 100 kilopascals. So you read those numbers, compute your U1, and finish the problem. All right? Okay. Does anybody have a question? Yes.
So on the midterm, we don't have to interpolate anything?
No, maybe you have to. Maybe you have to. But, you know, maybe it's something that you can do an eye interpolation. You don't have to get too fancy on the midterm, but definitely know how to interpolate. So, any other questions? Okay, let's do another one then. Let's make them a little bit more complicated. So in this one, in fact, let me just show this so I don't have to redraw this sketch. And again, this is another variation of a problem. So, and I think the 3107 is actually in the homework due next week. But this is a variation of it. It's not exactly the same, but it's the same process. Okay, so this is what is happening here. We have another tank. This tank is open, and there is a piston separating air at the bottom of the tank and water above the piston. But the tank is open, and the water fills the top portion to the rim. All right? And by the way, I think the difference between this variation and the original 3107 is that it's water on both sides. So it's water below and water above. But this one has air below because I want to show you something with gases. So, and then the data that we have is all written there. We're told that we can neglect the mass of the piston. We know the area of the cross-sectional area of the tank or the piston is 0.1 meters squared. We know the total height, 10 meters. We know the conditions for the air, which is at 300 Kelvin, and it occupies 0.3 cubic meters down here. And then what's happening is that now we're again going to heat this up. And of course, as we heat this up, the air is going to expand, and it's going to start pushing the water out. The water will start spilling out, and then we again are asked to find the heat transfer, the total heat transfer, after the piston has pushed all of the water out. All right? Okay, so that's the problem. How do we solve it? Okay, what is that? Let's figure out that we don't know much about the water, other than everything initially should be at 300 kelvins, 300 Kelvin. And it's another thing that I didn't tell you is that it's open to the atmosphere. It was in the diagram there. So it's open to atmospheric pressure above. Okay, so what do you think is the condition of this liquid water? Compressed liquid, because you know we're saying it is at 1 atmosphere basically, or near 1 atmosphere, 0.1 megapascals. Room temperature about 300 Kelvin. So this is compressed liquid. This water is compressed liquid. Even if it gets heated a little bit. Okay, so what about the air? What do we know about the air? We know the temperature and the volume, total volume. Right? We know those. Those were given. Can we find the pressure, for example? What is the pressure? Let me re-sketch the device here. So this is water. What is the pressure in the air? I'm sorry?
The force of all the water over the area of the cylinder.
Okay, plus the external pressure, right? So it should be the external pressure, right? Plus the weight of all this water divided by the area, right? So we did that already. But let's go ahead and write it down. So the weight of the water is rho G or rho V. Let's put VH2O times G. That's how much the water weighs, divided by the area of the piston. That's the pressure acting on the air, and therefore that's the pressure of the air. What is this? What is the volume occupied by the water? Is the total volume minus the volume occupied by the air, right? Okay, and that's of course neglecting the thickness of the piston, which we can go ahead and neglect. Okay, and of course the total volume is the area that was given to us times the total height this was also given to us. This h of 10 meters was given to us. So area times the height is the total volume. And what is the volume occupied by the air? Oh yeah, that was given. So so I can do this number. I know everything here. The density of the water. What is the density of water? Yeah, it's 1,000 kilograms per cubic meter. So that's given. And the volume occupied by, I'm sorry, what is the volume occupied by the water? I already plugged that in there. So I can get all of the initial volume of air. I can get the initial pressure of the air. Let's call it P sub 1, right? Because I have all the numbers. And if you plug in all the numbers, that will come out to be 170 kilopascals. So this is initial air pressure. All right? Okay, now one thing that we're going to have to figure out is what the PV diagram looks like. So if I plot P, and let's make it capital V, for the air, this is a PV diagram for the air. I start at a certain pressure, which we just calculated to be 170. So this is 1. And then where is it going to end? So what is the shape of the process? What do you think is the shape of the process path? And it has to do with this equation right here. Right? So if I grab this equation again and bring it down here, I can write P for the air is P naught plus rho. The volume occupied by the water, we wrote it here, is the volume occupied by the air, which is AH, minus, by the water minus the total volume minus the volume occupied by the air. Let's call it just V. And so that's that times G over A. And what is the shape of this equation? Well, you can group the constants together. This is P naught. Let's see what else is constant. A, H is the total height. That's constant times G. So I can add here rho A, H, G over A. Right? All the constant parts. And then I have left a minus rho G over A V. So this is the equation for the pressure of the air. Let me make that a little bit. All right. So all of this is constant. So therefore this equation is really the equation of a straight line. Right? This is a straight line. In terms of the volume of the occupied by the air. So what I know now is that, and it has a negative slope with the constant given by, the slope is rho G over A, negative. So I know that this has to come down like this. And let's say that this is the volume at which the piston is at the top. Therefore, that's my final state. So here is the initial volume, which was given. And here is the final volume when all the liquid is gone. So this one was given, the V1 was 0.3. Right? This was 0.3. And this one is the total volume, which is, the height is 10, the area is 0.1, so this is 1. This is in cubic meters. All right? And of course, I can also get this pressure because it's a straight line. So if I get that pressure, that number will be, let's see. Well, the final pressure, of course, is when it's at the top. Right? When it's at the very top, all that's left is atmospheric pressure. So this will be 100. This is in kilopascals. All right? So I got all the numbers in the plot. That means that I can compute this area, right? Which is, this is going to be the work, right, done by the air. So that work how can I find that area? Take the average pressure, right? So 1/2 of 170 plus 100, that's the average pressure. And then multiply times the volume variation, which is 0.7. So if you plug that in, you get 95 kilojoules for the work. So as the piston moves up, as the air pushes the piston up, it does 95 kilojoules of work. All right? And then, how do I find the heat transfer? Again, use the first law. So delta U equals Q12 minus W12. Solve for Q12. It's delta U, which is the mass of air, times U2 minus U1 plus W12. How do we get the mass of air? Was it given? No, but we have everything that we can use ideal gas law, right? So from ideal gas law for the air, right? So I can write P, let's write it V equals mRT. That's the specific constant for air. So I can get the mass is P1 V1 over R T1. And all of that is given. You can read the constant for R in the table. And if you plug this in, you get, see if I have it here, 0.59 kilograms. So I got the work, I got the mass. How about U2 and U1? The table for? No, there is one for air, right? There is an ideal gas table for air. Ideal gas table. There's two ways to finish the problem. I'm going to show you both of them. Ideal gas table for air, which allows me to read, remember, what is interesting about ideal gases is that the internal energy is only a function of temperature. So if I go to the table, it looks like that. We saw it last time. I have temperature entries, internal energies, enthalpies. So I need the internal energy. Since I know the initial temperature, which is room temperature, 300 Kelvin, I can just come in here and read U1 at 214.4. So U1 is 214.4 kilojoules per kilogram. I read that with T1, which was 300 Kelvin. All right? But I now need also U2, which means that I need T2. How can I get T2, the final temperature? Again, ideal gas law, right? So just grab it from here. So T2 is going to be now P2 V2 over mR. But again, we have P2 is 100 kilopascals, is 1 atmosphere. V2 is the total volume, which we have. So we can get this temperature, and this number comes out at almost 600. I have 597, but I'll round it to 600. Okay, it's 597, but 600 makes it easier to read the table. So if I go to 600, then I can go to the table at 600 Kelvin and read 435.1. So U2 for, what did I say? 35.1 kilojoules per kilogram. So now I got everything. I got the U1, the U2, everything, so I can find Q1, 2. And if you do it this way, you get 224 kilojoules. What's the other way to do this problem? So let's call this method 1. I guess starting here, right? The second way is how? How else can I do this problem? Suppose I don't have this table that gives me the internal energy as a function of temperature. What could I do? Nobody? From last time, last lecture? What could I do? No enthalpy. Because I would need a table for the enthalpy. But something else, another concept from the last lecture. The specific heat. So I can use the concept of specific heats. Remember that again, for an ideal gas, Cp, well, let's do, actually we need Cv. Cv is du dt. Right? And therefore, from there we got the expression that if we integrate this, we got that delta U is the integral from 1 to 2 of Cv dt, just by integrating that. But if we assume that it is a constant, assume Cv is constant, which, remember, it was reasonable if the temperature range was not very large, which it isn't in this case because we're going from 300 Kelvin to 600 Kelvin. In that figure that I show you, that's a very small range. So I can take it to be constant, and therefore I can compute the delta U as the mass. I'm missing the mass here. I need a mass here. M. Put a mass in there because this is capital U, not lowercase u. So this is, I need a mass right here. Otherwise I would have to write lowercase. So M Cv T2 minus T1. So I already have the temperatures, 300 and 600. I already have the mass. So the only other piece of information that I would need is the Cv. So I would have to have that, of course. Either I have that or I have the table. And the Cvs you find also in a table that we looked at a while back with ideal properties. So if you go to this table on page 760 and you look for air and look for Cv, and you can see it right there is about 0.72. So then you can plug that number in here. So this is, the mass was 0.59, 0.72 is the Cv, and the delta T is 300. So that will give you the delta U. And then you use that delta U in here instead of the one that we just got earlier. And you can finish this one up and look at, I don't have the number, you can do the number and see the difference between the two methods. Yes? Yeah, I had to put an M there because I left it out. This is an M. Because this is capital delta U. Okay, any other questions about this problem? So this is a little harder, yes?
So we're assuming that we're using the gas law for both of these.
For the air.
For the air.
At both ends.
Methods.
Yeah, for the entire process.
Is there any way where we have a situation where we would assume that that's very good?
Well, you know that the ideal gas law will break down if the pressure is very high. Right? So remember, in the case of air, you're looking for the highest component, which is nitrogen. Right? So if you look at nitrogen, where's nitrogen? Right here. You can see that the critical pressure is 3.3 megapascals. Right? So 3,300 kilopascals. And we are at 100 to 100 and some, right? So our pressure for our process is way below the critical pressure for nitrogen. And if you check oxygen, it'll be the same. So we are very safe. So unless the pressures are very high, you're safe using ideal gas law. Any other questions? Yes, back there. Oh, in the first law, right here. So you go back here, instead of reading U2 and U1 from the table, this becomes mCp delta T, right? When you solve it for using the first law. So in other words, what we're trying to do is compute delta U, And we can either do it directly from the table, if we have it, or if we have the CV with the delta T's. Any other? Okay. So one more. I think we have time. Like that. Okay, here's this one. And this is actually exactly no variation, but it's exactly this problem. 3230, I think it's in the homework. It's another heating problem, but different situation. So now we have the cylinder is fitted with a piston, but the piston is sitting on the stops, sitting there. And again, we have water, 1 kilogram of water. Given the temperature, 100 Celsius, the quality is 0.5. And then we're also told that to lift this piston, we need 300 kilopascals. And then the process is going to be heating the water until it reaches 300 Celsius. So water is there at 100 Celsius, is a saturated mixture of liquid and vapor. We're going to heat it up until it reaches 300. And probably we need to find Q among other things. Actually, these are the questions right here. First question is, at what temperature is all the liquid gone? So we're heating this up. We want to find out the temperature at which all the liquid is gone. And then we need to find the final pressure, the final specific volume, the total work done by the water, and the total heat transfer into the water. Not different from what we were doing, just variations. Okay, so what do you want to do first? You can see it right there. Underneath. Right? So always at least attempt to do a diagram. And here I got it all started for us. So here's a PV diagram, and I'll tell you what I did to put all these numbers that I put on it. So here's my initial state. I know it's a mixture because the quality is 0.5. Shrink this. So I know it's a mixture of liquid and vapor. It's at 100 Celsius, but I can go to the table and read the pressure. And I have that table here. So, well, actually, we need this saturated, which is right here. So I go to the saturated temperature table, go to 100 Celsius and read that the pressure is 101.3. It's about 1 atmosphere. So I put that there. At the initial condition, the pressure is 101.3 kilopascals. And I also put another line here for the 300 kilopascal pressure because I was told that's the pressure I need to lift that piston. So I put that there. That's just a horizontal line at 300. And then I put another couple of numbers here. I put the temperature. Remember, on a PV diagram, the temperature lines, the isothermal lines, come down from left to right. So they come high from the left side, intersect the saturation line, go across horizontally, and then go down again. So I put a couple of them, the ones that correspond to these two pressures. So I put the 100 Celsius temperature, which of course we know is our initial temperature, and then I put the one that corresponds to 300 because I wanted to have a measure of, you know, where that temperature is at 300 if it happens to be saturated, because I'm interested in knowing when all the liquid is gone. And that temperature that I read from the pressure table, so this is the pressure table. At 300, I marked it here, at 300 kilopascals is 133.5 Celsius. So that's the number that I put there. So that's what I have to begin with. So now that I have done that, I should then find some numbers. And what numbers should I determine first? That is actually missing in this chart. This, right? This initial specific volume. But that's easy because we have the temperature and we have the table. So that initial volume, initial specific volume at 100 Celsius is Vf plus X Vfg. I have everything, so I can determine that 0.837. And I can put it in this chart, 0.837. All right. Okay, so now where does the process take me? I start heating this thing up. Which direction does the process go? It goes up, right? Because I have a pressure of 101. I cannot lift that piston. So I have to keep going up at a constant volume. I cannot lift that piston unless I reach 300. So I know I'm going to start that way. Okay. What is another piece of information that is useful here? Well, we should find out the V sub G at 300, because that's important, right? Because that's when 300 is when the piston will begin to lift. So if I go to the table, to the same table at 300, which is the one that I marked for the temperature. So at 300 kilopascals, I picked that temperature to put on the chart, but I can also read the V sub G and see that the V sub G is 0.606. 0.606. And of course, that's less than this. So I know that this volume here is 0.06. Sorry. It's less than the one I'm starting with. So this volume, if I can bring it down here, right? This one is 0.606. So I know it's to the left. All right? So that, of course, tells me that I'm not going to reach 300 until I get out of the dome. Because I'm going to reach, if I keep drawing this line up, when I reach 300, right, which is when the piston will begin to lift, I'm already outside the dome. So all the liquid is gone. So I have to step back and say, well, so how do I answer the first question? At what temperature is all the liquid gone? Obviously, it happened before we hit that intermediate stop right here. Let's put it in black. Because all the liquid is gone right here. Right? That's when all the liquid is gone. And how do I determine that temperature? When all the liquid is gone. Find a VG of 0.837. That is correct. So if I come here, right, same table, but now I'm looking only at the VG and I need 0.837, and finally we hit a place where there is not an exact number, right? So those of you who didn't want to interpolate. So 0.837 is between these two, right? But it's not close enough to either one for me to say, well, I'll take one or the other. So I have to do a little bit of a fancier interpolation. So I'm going, one is 0.79, the other one is 0.88, and I need 0.84. So I kind of eyeballed the two. I said that it was 122. All right. I'm sorry. If I said that, oh no, that's fine. Temperature-wise. So here's the two temperatures. Right? It has to be between 120 and 124. So it's not a huge temperature difference. Right? I figured it was more or less in the middle. So I picked 122. So the answer to this question for me was 120, approximately 122 degrees Celsius. Right? When all the liquid is gone. Okay, now, so I hit the 300 pressure, the 300 kilopascal pressure. But certainly I am still not at, because now I'm going to be lifting the piston. Let's put all this stuff away here. All right. And so this temperature is still not yet the one that I need, which is 300. So I know I need to get to 300. So, but of course now the piston is rising. So now the process is a constant pressure process. So I just keep, I need to now make a sharp turn to the right and keep going until I reach a temperature of 300. So I'm going to finish here. That's really my final state, where I intersect the line that is missing here, which is the line for 300 degrees Celsius. All right. 300 Celsius. So, all right. So now we can answer some of these other questions. What's the final pressure? It has to be 300, right? Because once we hit 300, we don't go any higher. We stay at 300. So P2 is 300. What's the final specific volume? Now we need to go to the superheated table. So if we go to the superheated table at 300 kilopascals, right here, 300 kilopascals and 300 Celsius, we need that number, 0.875. 0.875. So this volume right here, which is at the end of the process, is 0.875. All right. So I started at 0.837, went up to 0.875 for the specific volume. So maybe answer these questions here. So P2 is 300 kilopascals. V2 is 0.875 cubic meters per kilogram. What about W12? What's W12? Here's 2. What is the work in this graph? You agree that it's just the area under this line, right? Under the horizontal line? That's the work. Right? So the work will be that pressure, which is the top line, the height, and then the width is the delta V, right? And of course times the mass. So let's write just V2 minus V1 times the mass. The mass was given, it was 1 kilogram. So that'll be the work. You can get the number. And then the heat transfer, Q12. Again, first law. So we do always the first law last. So following the other two problems is a similar result, right? So this will be delta U plus W12. The delta U is M U2 minus U1 plus W12. So we have the work, we have the mass, U2 and U1. U1, you go back to the saturated table, read UF and UFG. get your U1, and U2, go back to the superheated table where we just read the V2 and read also the U value, the lowercase u value. So you plug the numbers in there and you get your heat transfer. All right, so this is perhaps a little bit harder. All right, we still have time, so anybody has a question about these problems? No questions? All right, so let's do one other thing. Which is, I want you to, we need to derive a rate form of our first law of thermodynamics so that we can use it in the following chapters. So there is really not much new here. Here is a certain process. I didn't put any particular properties, any two properties and a process just like the ones we have seen. So I'm going from state 1 to state 2 on that red dashed line. And I also drew a little segment of the line. And on that little segment of the line, there is an infinitesimal change, which is just dE. Remember, we were talking about the difference between delta E and dE. Right? So if we put the delta E, the total delta E is, of course, E2 minus E1. That's from beginning to end, from 1 to 2. But if I just take a small segment of the path, an infinitesimal segment of the path, then we're talking about dE. Okay, now, we have the first law. And notice that I'm using total energy. In these three problems that we solved, we used internal energy because we weren't neglecting anything else. But if you want to write the complete first law, then you write E for total energy. But it's the same equation, delta E Q12 minus W12. But I can also write it for the infinitesimal segment. So the first red box has the first law of thermodynamics for the entire process. The second box has the first law of thermodynamics for the infinitesimal path. Obviously, it really is the same thing because to go from the second equation to the first equation, all I need to do is integrate. If I integrate the second equation from 1 to 2, I get the first equation. All right? Now, the idea of developing a rate form of the equation is because we might be interested in knowing what is happening per unit time. And neither of these equations tells us anything about what's happening per unit time because we're just looking at the total change. Total change from 1 to 2 or total infinitesimal change. But if the infinitesimal change happened over an infinitesimal time that I can measure, then I can divide by the time the second equation. If I divide the second equation by the time, I get that. I get dE over dt equals delta Q over dt minus delta W over dt. And now I have what is known as the rate form of the equation. For short, we write the rate of heat transfer, that is delta Q over dt, we write it as Q dot. So the dot we have seen before is just there to tell us per unit time. The same thing for the work. So the delta W over dt, we just write it as W dot. So that's now power, for example. This would have units of energy per unit time, units of power. Of course, these too. Q dot has units of power. The left-hand side, dE dt, we just leave it like that. So we could write E dot, but we don't. We just write dE dt because there are problems in which we're going to have to integrate again, and it's more convenient to leave it like that. But it's the time variation of the time rate of variation of the energy during that little segment. So this we refer to as the rate form of the first law. And you should be familiar with all three. You should be able to, depending on the problem that you're solving, at least the first and the last one. This is sort of an intermediate step right here. The global form for total change from beginning to end, or the rate form, which is valid at an instant in time if you're actually interested in measuring rates. Okay, in the few minutes that I have left, I'm just going to ask you a few questions. So get ready. Get that on. Okay, that one is from last time. Okay, that's the last question from last time. That's just for you to get ready. So the first question is coming up next. And it's a question about specific heat. So specific heat at constant pressure is independent of temperature for A, all ideal gases, B, monatomic ideal gases, C, diatomic ideal gases, D, none of the above. And I'm going to close it quickly because this is an easy one. So 5, 4, 3, 2, 1, and 0. All right? I'm going to see if it's true that you think this is an easy one. Not very much. Correct answer is B. Monoatomic ideal gases. This is something that we saw on Tuesday. See if I can find it quickly. This chart. Right, showing the specific heat versus temperature for different ideal gases. This is all ideal gases, but the only ones for which you can see clearly that the specific heat is a constant are the monatomic gases. So that was that one. Any questions? That one was, I thought it was easy, but let's do another one. Close that. Okay, another quick one. Water at 200 Celsius and 300 kilopascals. You think it is compressed liquid, saturated vapor, or superheated vapor? Just off the top of your head. 5, 4, 3, 2, 1, 0. All right? Off the top of your head. Oops, I made the same mistake last time. Let's delete that one. All right, what did we do last time? We went back. Go to the graph. So this is the second. The thing is just on for a little bit and you guys are already firing. Okay, this is what you said. Wow, look at that. So, yeah, D is correct. Superheated vapor. All right, 200 Celsius and 300 kilopascals. This is just to see if you already have some of these numbers in your head from doing problems. But the only way to find out for sure, of course, is to go to the table. But okay, let's see. Any questions about this one? Anybody? If you don't believe it, of course, go to the table. Let's see. Let's do another one. Let's do one more. Maybe we can do two more. How about that one? True or false? W12 is equal to W2 minus W1. Five, 4, 3, 2, 1, 0. Okay, let's see. Yeah, it is false. W12 is not equal to W2 minus W1. Why is that for the 39 who said that it was true? Because that would imply that W2 and W1 are states, right? And there is not a state W2 or a state W1. There is no work at state 1 or work at state 2. There's just working going from 1 to 2. Okay, and let's do one more, just one more. Let's see, we did that one. Okay, what is the critical temperature of water? Approximately. Fast before you look it up. 5, 4, 3, 2, 1, 0. Again, this is just, you either have to look it up or just have an idea already. It's not your first choice or your second choice or not even your third choice. The right answer is 374. And you can see that, of course, if you go to the table. If you go to the saturated table, it's always the last entry in the temperature table, 374. All right, I'll see you next week.